So if you haven't heard, there's actually a lockdown going on, which means people get separated. And when people get separated, they get lonely. And when they get lonely, they use dating apps. Recently, after I had a bit of a frustration with multiple dating apps, I suddenly had an idea. Why not build my own dating app? That way, I could be the admin, which is basically the god of the dating app, and match whoever I want. Now, at this point, I thought dating apps are just about swiping, some texting, and maybe some cool designs. Easy. I should be able to do that, right? But then I came across a problem. One I had not thought of before. A problem that every single dating app out there has to solve, but also a problem you most likely have never even thought of before. Want to know which? Stick with me. So imagine you made a dating app. You have users across the world signing up for your app because you made such a nice design, which is why everybody loves to download it. Yay! However, now you get to do what every dating app does. You actually have to match people with each other. Now, of course, you don't just want to match everybody with everybody, because for most people it's not really interesting to match with people that are on the other side of the globe, where the chance of meeting them in real life later on is really low. Therefore, you want to be able to give your user the possibility to define a radius in which they care about meeting people. And then only if two users are in the same radius of each other, they can see each other in the dating app and have the possibility to match later on. Now this arises a problem you have probably never thought of before. How do you actually check who is in the radius of who? I mean, sure, if you just have Ben and Anna, it's easy. You just check the distance that's between them, and then you do a simple check if the distance between them is smaller than both of their radius, and you're good. Super easy, right? Well, yes, if you only have two users, this is not even a real problem. But now imagine your dating app is really popping, and instead of 2 users, you have 1 million users. Now, if you were to approach this the same way you approached it with 2 users, you would have to compare one user to the next user and the next user to the next user and so on. Now, only for this one user, this would already mean you will have to calculate the distance function 1 million times. And then for the next user, you would have to do these 1 million calculations again. And if you want to get all users, you end up with 1 million times 1 million until you know all the distances and who is matchable with each other. In other words, the time your algorithm needs increases exponentially, and that is never a good thing. You also got to remember that users don't just publish their location once, but constantly during the day while they are moving through their city. So this means the location comparison does have to happen constantly, which means it has to be fast. This gives us the challenge to develop an algorithm that can identify all of the users that are within each other's radiuses while being really fast. So let's try to optimize our approach from before till we get an acceptable result, shall we? So first off, let's have a look on how we actually calculate the distance between 2 users. Now, the distance on Earth can be calculated by something called the Haversine formula, which basically consists of squaring, cosinus, sinus, pi multiplication, and a bunch of other complicated and computing-intensive math stuff, which in code can look like this. Why is it so complicated to calculate the distance between 2 points on Earth, you ask? Well, against popular belief, the Earth is actually not flat. So if you want to get an accurate distance between 2 points, you basically have to calculate the length of a line on a sphere, and when you try to think deeper about it, that's actually not quite straightforward. Back to the algorithm. If we were to implement the algorithm in its most stupid form, we would go through the users one by one and say, okay, this user A, then do the Haversine formula and calculate the distance between him and number 2 and check if the distance between them is smaller than both of their radiuses, and if so, we can mark them as matchable. We then do the same thing with user B and so on, until we know for every user if they are matchable or not. As you can already imagine, this is super time intensive once we get a lot of users. We will do 3 tests, one with 1,000 users, one with 10,000 users, and one with 100,000 users, and compare the time the algorithm needs to calculate all the matches. And then once we optimize the algorithm, we will run the same tests again to see how much we have improved. So I went ahead and implemented the basic algorithm, which compares each user with each user using the Haversine formula. And this is what I got. For 1,000 users, the algorithm took 61 milliseconds. For 10,000 users, the algorithm took 5,010 milliseconds. And with 100,000 users, it takes more than 500,000 milliseconds, which is actually a bit more than 8 minutes. So as explained earlier, the time the algorithm needs rises exponentially with the amount of users. With 1 million users, the time needed could actually increase to hours, which is why I did not include this in my test setup. So not really usable for an app with millions of users. So let's have a look on how we can optimize this. The first easy quick win option is actually to become a flat earther and just assume that the Earth is flat and change our Haversine formula to the Pythagoras formula, which gives us the distance between 2 points on a flat surface. The Pythagoras formula is actually much easier and takes way less time to compute. The drawback is that for greater distances on Earth, this results in inaccurate distances because it does not consider the curvature of the Earth. However, usually dating apps like Tinder or Bumble only allow radiuses of around 100 kilometers plus, and for those distances, the Earth curvature does not really matter. So let's kick out the Haversine formula and check out the Pythagoras one. I now ran the same benchmarks as before, and this is what I got. For 1,000 users, the Haversine took 61 milliseconds, while the Pythagoras one took 34 milliseconds. For the 10K users, the Haversine took 5,010 and the Pythagoras one 2,328. And for the 100K, the Haversine took over 500,000, while the Pythagoras one only took 190,000. So already a lot better. But the big issue here is that the time this algorithm takes still exponentially increases with the number of users that are getting checked, which of course is still not a good thing. So how can we fix that? Well, the next idea would be to split the users into groups. Because of course it makes no sense to even compare all the users together if one of them is in Australia and the other one in the US. But how can you make this split? How can we define which users should actually be compared and which don't? Well, you might say, why don't we just split them by countries? And only if 2 users are in the same country, we do a comparison. If we were to split these users by countries, what would happen if a user in, for instance, Germany lives right on the border to France, and next to him, across the border, live all these beautiful French girls. But then, because of the split by country that we do, he would never be able to meet them, which will probably be a reason for him to sue us, which I would totally understand. The same applies if we would do the splits by city or state, so just simply splitting it like that does not really work. However, I still found that splitting will probably be the only real answer to the problem. However, we will have to do it in a bit more advanced way. So imagine the whole world as a 2D coordinate system, but instead of using X and Y, we are using longitude and latitude. In this coordinate system, we then get all the locations of our users. We then look for the outmost locations to define a rectangle which includes all of the users. So, for example, we take the latitude from this guy, since he has the lowest latitude and the lowest longitude from this girl. If we then combine them together, we get point A of our rectangle that will fit all of the users. We do this the same way to get the other points of our rectangle, so now we end up with this beautiful rectangle. After we have our rectangle, we can split it into evenly matched cubes. This graphic is of course simplified because in the real world we would have a much larger number of cubes. We can then go ahead and compare all the users which are in the same cube to each other. After that, we can get rid of all the users which radiuses are not over the border of the cubes. So we only want to be left with users which radiuses are overlapping with the border of their cube. So for example, let's say we have cube B and A, and in there are these 3 users. Now when we check these 3 users, we notice that their radius overlaps with the other cube. That means the user can potentially be matched with users from the other cube. We then create a new cross or overlapping cube called AB and put all of the users that have an overlap between these cubes in the new cube, and then calculate the distances between all the users in cube AB. When we do this for all cubes, we will only compare users which have a high probability of being in each other's radius, because our goal is to perform the least amount of distance calculations as possible. Now, to be fair, implementing this code took a lot longer than the last 2 approaches, but of course I handled it just like a boss. The measurements we get with this are the following. 59 milliseconds for 1K users, which is actually expected since the time it takes to create the cubes actually makes the approach less efficient for low numbers of users. But then for 10K users, this approach only took 968 milliseconds, so less than a second, in comparison to the other two, which took 5 or 2 seconds. For 100K users, it took roughly 65,000 milliseconds, which is roughly a 700% increase in performance. Well, this was my little take on solving this problem. There are, of course, much more advanced solutions for this, which I will explore in future videos, but that's it for this video today. So if you like this video, please give it a thumbs up, subscribe if you like more of this content, and also comment down below if you have any questions.